This video deals with Newton's third law, which states, for every action force, you have an equal but opposite reaction force. And this is kind of a law that can be confusing because it's not always as obvious as the other two laws were. And the reason is this whole idea of equal but opposite. If I have one force, I have to have another force that works in the opposite direction that's the exact same size. You know, an example of this might be just simply, let's say we're pushing a wagon. So here's our little red wagon, little red wheels. I'm going to push on this with the green hand. So maybe this is an alien pushing our red wagon. Or whatever. The idea is we have two different forces that are now acting on this. We have a force that's going forward. That would be the force of my hand. But I have to have another force going back according to this law. That would be the force from the wagon. Now, if you think about this, this probably makes a little bit of sense. When you push against something, you feel your hand get some pressure from that. Or it compresses or kind of gets pushed together. And that's the force of that hand, or the force of the wagon pushing back against your hand. The question is, why is there movement then? So if both of these forces, these two things are equal, how can there be movement? Well, typically your hand is pushing against something else that is attached to, like your body, which has more mass, which means it'll have more inertia. So this this wagon here will have less inertia and will get pushed forward. So another kind of simple example about this is like a hammer and a nail. If I just simply draw a very simple nail right here, and then I attempt to draw a hammer. There's two forces that are going on with this. And what I'll usually ask is, how does the force of the hammer compare with the force of the nail? And it's the same kind of idea where we know that the hammer is going to be driving that down. And according to Newton, the force of this hammer going down is going to be exactly equal to the force of that nail. It's supposed to be N there, sorry. Coming back up. And then that's where it can be a little confusing. If I have equal forces, one going up, one going down, how does this nail get driven into the wood? Because if you've ever tried to do any little simple carpentry, you know that once you hit a hammer with a nail, that this thing goes flying down. And again, this has to do with the hammerhead here having more mass. More mass equals more inertia again, which causes the overall movement of the system here to move downward. So that's how the nail gets driven down. It has less inertia than the hammer. It takes more. It would take more force than this nail can generate. It can only generate as much force as it's hit with to make this hammer stop at exactly where it is. So that's why when you hit a hammer into a nail, the nail goes down. That's why you want to have some mass in this hammer. You can't have too massive of a hammer because it would be too hard to swing. But you wouldn't want to hit a nail with a similar sized hammer compared to the nail. Another way of looking at this is somebody that is walking. If this is an over curve of the earth here, and this is somebody's foot, and this is going to be a little ugly, so bear with me here. But the idea here is somebody's knee, whatever. But when you walk, the direction you push is backwards. This would be the force of your foot. But you want to go forwards. We know from Newton's second law, which was F equals ma, in order for us to move forward, we have to have some type of accelerating force. So for us to move forward, we have to have something pushing against us. And in this case, it's the earth. The earth pushes us forward. And again, equal forces. Whatever we push back, the earth pushes forward. Well, we have really very little mass compared to the earth, which has a massive mass. Which just kind of says, even though we're pushing with equal and opposite forces, there's just so much more earth than there is us when we're walking that we are going to move forward. The earth does go back, and it goes back with the same idea of this F equals ma. But the acceleration of the earth is so tiny that we don't really notice this. So the two things that we kind of noted so far is forces always happen in pairs. And the motion that occurs from these things is usually due to a difference in inertia. Okay, so the third law basically lets us know that there's always going to be two forces, and these are kind of two extra little descriptive things to help us understand those things a little bit more. Two more examples we're just going to kind of talk about is planes and rockets. If this plane is flying, it's not touching the earth. Its propeller here is generating a forward thrust, but in order for that to happen, it pushes air backwards. So we know that that's the force of the plane pushing air. Your reaction force, which we'll draw in red, is just simply then the air pushing the plane. And that's kind of the idea of flight. As long as you have this propeller turning, it's going to pull the plane forward by pushing backwards on the air. When rockets launch into space, there's not air present. So I want you to think about when a rocket's launching, how does it move, or what does it have to do? Well, to kind of help you answer that, we know back here's the rocket boosters or the rocket engines that push it. Typically, when they're first taking off, you'll see a lot of like smoke and stuff like that coming out of here. Obviously, this is not doing the same thing. But when they first take off, that is basically fuel getting burned up. So the rocket pushes the fuel back. And by now, we hopefully understand now that the fuel pushes the rocket forward. So that's how they can fly in space. There's no air to push like with an airplane, but there is something else, and that's why rockets tend to have big fuel tanks, especially to get out of the Earth's atmosphere. It takes a lot of force to push this much of a massive object through the Earth's gravity and be able to escape that. So that's, in a real simple form, Newton's third law.